Today, I will be discussing equilibrium of a particle, the free body diagrams and how to draw it, and a coplanar force systems. Okay, so our objective today is to learn about how to draw a free body diagram and apply equations of equilibrium to solve a two-dimensional problems. We would do certain activities today as before. There's a reading quiz, there are applications, and why, and how of a free body diagram. We're going to talk about equations of equilibrium, analysis of spring and pulleys, a concept quiz, a group problem solving, and a tension quiz to wrap everything up. So, when you can read this with me, again, this is a reading quiz, and I will give you the answer shortly, but let's talk about that a little bit. Okay, I'm trying to pull it up here. Okay, great. So, when a particle is in equilibrium, the sum of the forces acting on it equals to A, a constant, B, a positive number, C, 0, a negative number, and an integer. In order for a particle or a body to be in equilibrium, the sum of the forces acting on it must be 0, otherwise the body is not going to be in static, it will be, the body won't be stationary, it will be in a dynamic position. The second question here is for a frictionless pulleys and cable. Tensions in the cable T1 and T2 are created by what? So we have a frictionless pulley and cable, and we apply two forces T1 and T2. They are both in tension. That is an equivalent to saying that there is an object hanging by T1 or from the cable that carries T1, and we actually try to pull that object up by a force T1, by a pulling force that, or what we call tension, that we put on the other side of the cable, and as such, there's an angle that you see theta, and that is associated with that right there. So, if the pulley and cable, there's no friction involved with them, they're frictionless, then the tensions in the cables T1 and T2 are, we try to come up to see which one is the correct answer. So, T1 is greater than T2, T1 is equal to T2, T1 is smaller than T2, and T1 is T2 sine of theta. Well, as you can see, all the forces in T2 must be balanced by another force. Again, the summation of forces in the y direction, in this case, we're going to discuss that later. But obviously, in this case, in order to balance T1, and because the pulley and cable, they're frictionless, T1 must be T2. Now, we must be equal to T2. Now, that's the magnitude of T1 and T2. So make sure you keep that in mind, although there's an angle theta involved, but these forces must be equal, otherwise the system is not going to be in equilibrium condition. Okay, so let me move on and talk a little bit about where is it that we apply equilibrium of a particle, equilibrium of an object, and so on. Here's an example of a crane. The crane is lifting a load. To decide if the straps holding the load to the crane hook will fail, we need to know the forces in the strap. After we know the force in the strap, then we can design the strap properly, or use a strap that has enough strength to be able to carry the force that's caused in T1. So how could you find the forces in T1? Now there are three straps that are connecting the load to the end of the crane. So here's an example of where we use equilibrium to pretty much design a cable. Again, this is a simpler application, but the more advanced application would also be coming either today or later. We're going to discuss about more advanced applications. Another application is also presented as you see here. So another application is for a given spool with certain weights, as you can see here. Again, we are trying to lift this by a crane. It is connected at points B and C to a cable system. B and C, they're connected to A, and D is shown the end of the crane. So if we have a spool of given weight, how would you find the forces in cables A, B, and AC? If designing a spreader bar like this one, this is called a spreader bar, and we need to obviously know the forces at B and C, the forces that will be developed in this bar, so we can design it in such a way that it doesn't fail. Imagine that if we don't design, again, in this case it's a bar, but you can imagine that if we are not able to use our principles of statics or other science to calculate this type of a force in a bar, you can imagine if it fails, what kind of a devastating effect it might have. This is a smaller example, but think about our structures, our bridges, and other types of buildings that we have. If we really cannot afford any of them to fail whatsoever. So statics is really an important foundation for any kind of a design that we do. It really starts with statics. So one application of statics is to design such a spreader bar in this case so it won't fail. Okay, so that's something important to realize. Okay, so let me move on and here's the way it is shown. Shortly, we're going to talk about a free body diagram, but a free body diagram is nothing but a graphical representation of the forces that would develop in such a system. Again, point A is shown here. W is the entire weight, and the T sub A, T sub B, and T sub C are the tensions in cables B and C, respectively. Another example, for a given force exerted on the boat's towing pendant, that's also provided here. What are the forces in the brittle cables? And that's, you can see that is also another application. What size of cable must be used so we can safely perform this operation. Okay. What is a coplanar force system? Again, it's a planar, add co to it, coplanar force systems, and the right way to pronounce it. This is an example of a 2D or coplanar force system. And that means all of these forces, they would go through one point. They are in the same plane. They're all in the same plane. So if the whole assembly is in equilibrium, then particle A is also in equilibrium. So again, I repeat that. If the entire assembly, the entire system is in equilibrium, the particle A is also in equilibrium. Every time in statics we talk about a system, we talk about an assembly, we talk about group of members, a group of again different sections. They come together for a certain reason. We call that a system or an assembly. So if the entire system is not moving, it's in equilibrium, then particle A, and the point in which all these forces they coincide, they must also be in equilibrium. So in order for us to determine the tensions in the cables for a given weight of the cylinder, we need to learn how we can actually draw a free body diagram and apply the appropriate equations of equilibrium in order to be able to do so. So if you want to draw the free body diagram for this assembly or the system, simply we replace the cables by the forces that are presenting in them. This would be shown by one arrow. Also this one should be shown by one arrow, and this one would be shown by one arrow. For example, for this arrow we would show the force as 40, and for the other arrows we can, if they're unknown, we can just show them a T sub D, a tension in cable, or T sub AD, or in this case we can call it T sub AB. Let me see if I can. This is A. Not bad. Okay, and T sub A D. Okay, and so on. So again, free body diagram is essential in solving a statics problem. It is a graphical representation of all the external forces acting on the particle or on the system. And again, it would simplify the problem. It really helps us to solve for the unknowns in a much faster and more efficient way. So how do we draw the free body diagram? First, we imagine that this particle or this joint is isolated or cut off from its surrounding. In this case, the cylinder of the mass is 40 kilogram. And as shown, again, it's the much better graphical representation of what I just had. And let me go back here. Okay. So first we isolate the particle from its surrounding environment and show it as A. And then we would show all the forces that are acting on the particle at A or on A. Again, the known force in this case is shown by blue, and the unknown ones are shown by red. And we put our coordinate system right at A, the way it's shown here, X and Y. We can really put X and Y in different places, but in this case, it seems to be more convenient. And Y would be our 40 kilogram cylinder mass would be the continuation of Y downward, so it's going to be a negative Y, and the tension that shows in cable AD, T sub AD, is actually set on the negative position of X, so that's minus in the minus X direction, or in the negative direction of X axis. So this is really how we can show that. Now, there are active forces and reactive forces. Let's define them now. The active forces, they want to move the particle, and the reactive forces, it's the reaction, and they tend to resist the particle in motion. So we show both of them here. Now, after we do that, we identify each force and show all known magnitudes and directions. And the one that we know we put it on the free body diagram accordingly. In this case, F sub C is 392.4 Newton when the mass is 40 kilogram. That's Newton is the force unit for force in SI systems. So then we show all the unknowns as well, F sub B and F sub D, or T sub AB or T sub AD as such. Then we would use the equations of equilibrium. These are 2D equilibrium, and Newton's second law would be used here as an equation. The equations that are developed here, they're based on the Newton's second law. That's the Newtonian mechanics. Particle A is in equilibrium. Then the net force at A is also in equilibrium, meaning that the net A is also in equilibrium because the entire system is in equilibrium. As such, the net force at A must be 0. So F sub B plus F sub C plus F sub D is 0. Note that we have not considered the direction of the forces yet. Any of them that are acting in the negative direction of X, they will be shown as negative, and those that would be acting in the negative direction of Y should be shown as negative. X and Y, X is positive to the right and Y is positive upward. That's the sign convention we use, the Cartesian coordinate system. In this case, summation of forces must be 0 because the system is in equilibrium. All the forces, they go around A, so at A, the summation of forces must be 0. Now, the forces that are acting at any point in this system is also, the summation of all those forces must also be 0. So in general, for a particle in equilibrium, the summation of forces is 0, or the summation of force, in this case, in vector notation, the summation of force F sub xi plus summation of force F sub yj. I and j was the unit vectors in the x and y direction, must be 0, and so on. So this is the way we actually show it in the vector equation. In this case, if we take a look at the summation of forces in the x direction, in this case, because we're talking about a particle, it would be also 0i plus 0j. In scalar form, summation of forces in the x direction is 0, in the y is 0. Again, there are equations for equilibrium, and that could be expressed both in vector and in scalar form. And again, we can solve these for the two unknowns that we have and calculate F sub B and F sub D accordingly. So let's take a look at this example. Let's continue with this. We are going to look at our free body diagram at A. F sub B, F sub D, and F sub C is shown. F sub C is known. F sub B and F sub D is not known. We take the summation of the forces in the x direction. In the x direction, we have F sub D. Okay. This is our F sub D acting in the x direction, and also the x component of F sub B. Okay. Also acting in the x direction. One is in the positive direction, the other one is in the negative direction. The x component of F sub B is simply F sub B cosine of 30, knowing this angle. So we know this one acting in the positive direction. F sub D is acting in the negative direction, so it carries a sign negative, and that must be 0. Again, summation of forces in the x and in y must be 0 for a system or for a particle to be in equilibrium, to be in static equilibrium. So what about F sub y direction? The summation of forces F in the y direction must also be 0. In that case, we have one component, which is F sub C acting downward, 392.4, so that's negative. And there is also a y component of force F sub b, which is F sub b sine theta degrees. Okay, that's also acting upward, and that also we set that to 0. So from here, right away, we can calculate F sub b as 392.4 divided by sine of 30, and F sub b should be 700. This is from this equation, the equation number 2. We calculate the answer number 2, and the answer number 1 is also calculated after we back substitute F sub b into equation number 1, shown here by 1, and then we can calculate F sub d as 680 Newton. That is equation number 1. Well, answer number 1 calculated from equation number 1. So this should be pretty straightforward, setting up summation of forces in the x, set it to 0, taking the summation of forces in the y, and set that to 0. What about for the cases of springs, the cables, and pulleys? Let's take a look at the spring example first. Springs are used for many different reasons. They're also used in modeling. The stiffness of a spring shown by K is also shown, also used in modeling our structures many times. I've seen it many times. So the spring constant, or stiffness, what I call stiffness, is K, and that is different for different spring depending on the material. The spring constant K is different. If we multiply that by deformation, in this case it's shown by S, it can also be shown by D, shown by delta, shown by different symbols. So a spring force is proportionate by its constant and its deformation. So every time we multiply these two together, the spring constant by the displacement that the spring can go under, that would give us the force. So force in the spring is K times S. This is very important formulas to memorize, really. Then for the cable, if there is a friction pulley, as I mentioned previously, T1 is equal to T2. So these are the principles that we use throughout our calculations as an extra equation to solve our problems. In many cases, we may have more unknowns than the available equations. In that case, the structure would be indeterminate, but with the help of principles of, in this case, spring force and the friction, we can equate that and solve some of our determinant structures. So here's an example. I want you to review this example with me before we can start solving and go over the example. Okay, so the cylinder E weighs 30 pounds and the geometry is shown here. And we would like to find the forces in the cables and weight of the cylinder F. So the angles are given, the assembly is given, points of reactions are given, A and D. At point of contact, they're pretty much, these are the supports for A and D. At A and D, these would support the structure. There's a 30-pound weight at E, and F is also unknown. So we would like to find both forces in the cables and the weight of the cylinder F, knowing the 30-pound weight of E. So the first thing we do is we would draw a free body diagram for point C. If we can find the forces in cable CB, CD, and in CE, which is 30 pounds, then we can easily go ahead and set another free body diagram if needed and calculate the weights in the force in AB, because if we calculate force in CB by having setting up the free diagram, at C, and then if we calculate this force in this cable, obviously we find the force in the other in cable 2, and then from there on, knowing this force, we can easily calculate this force up here. So let's tackle the problem. So here's, again, take a look at point C. Here's the free body diagram at point C. It should look like the one at the left. Forces are shown, the angles are shown, X and Y coordinate system is shown. The weight of 30 pounds acting downward along Y in the negative direction is also shown. We take the scalar E of E R, the way we actually show it. Again, we would set the equilibrium equations. Summation of forces in the X is set to be 0. In the X direction, we have F sub BC cosine of 15 minus F sub CD cosine of 30. In the X direction, right, we have the X component of F sub BC, and we have the X component of F sub CD. One is acting negative here, and one is acting positive. The other equation in the Y direction, we have a 30 pounds known, that's negative sign acting downward, and there are two other forces. They are the Y component of F sub B, F sub BCY. The Y component of F sub BC would be F sub BC sine of 15 degrees, right? And for the Y component of F sub CD, the Y component of F sub CD would be F sub CD sine of 30 degrees. Again, this is positive acting upward. This is negative acting downward. We set that equal to 0, and we solve these two simultaneous equations for the two unknowns, F sub BD and F sub CD. Basically, we express one unknown in terms of the other one, and then we use that unknown, we plug it in to the other equations, and we solve for we only have two unknowns, two equations. We can easily solve that equation. So F sub BC would be 100.4 pounds, and F sub CD would be 112 pounds. And knowing these, now we're going to go back to point B, again at ring B, and this is B. Okay, we're going to go back to B now. We set the free body diagram as such. Again, we take the summation of forces in the X, we set that to 0. F sub BA, F force is going from B to A. That's how we usually show it. F sub BC, it's the force that acting from B to C, F sub BC, and F sub BA. F sub BC is known, W sub F is unknown, and F sub BA is unknown. We have two equations, two unknowns. We solve these two simultaneous equations to calculate for the unknown, which is F sub BA and W sub F. Again, summation of forces in the X is set to 0. F sub BA cosine 45, acting in the positive direction of X. That's the X component of F sub BA. And then there's also the Y component of F sub BA acting upward. So we set these equations basically, and we solve them simultaneously and find the answer to our unknown. So let's take a look at a concept question here. Again, this is very interesting questions I have here for you. and that is assuming you know the geometry of the ropes as shown. You cannot determine the forces in the cables in which system above. So, why? So if you know the geometry, you cannot determine the forces in the cables in the systems above. Why not? Well, the weight is too heavy. That's reason number one. The cables are too thin. Reason number two. There are more unknowns than equations. Reason number three. And there are too few cables for a 1,000-pound weight. Well, the reason is not A, not B, not D, but C, because in this case we have 4 cables, and we actually cannot solve it because in this case the 4 equations, 4 unknowns, we can only have 2 equations. Later on you see that we can add the moment equation, we can throw that in, but still we have too many unknowns, and we cannot, we have more unknowns than the available equations, so we seek to solve these problems using other methods. If you take advanced structural analysis later, courses like that, then you'll be able to use indeterminate methods of moment distribution, the energy methods, and all those methods to solve for problems like this. So let's take a look at this group problem. We look at it together, and then we're going to do a concept quiz, and we wrap this session. So the box weighs 550 pounds, and geometry is also shown. And we would like to find the forces in the ropes AB and AC. As before, let's develop some kind of a strategy. We draw a free body diagram for point A, and then we apply our equations, and we will solve for AB and A sub C. First, we draw the free body diagram at point A. All the forces, including the weight of 550 pounds, is shown here. And as you can see, we put the, in this case, it's the ratio of the triangle is given. It's a 3, 4, 5 triangle, and the angle of F sub B with the x direction, although acting in the negative x direction, is also 30 degrees. So applying the scalar at A, we get summation of forces in the x's is 0. We set summation of forces in the y is 0. And then as such, we have 2 equations, 2 unknowns. We can easily solve for the unknowns. Okay, this is an attention quiz here. We would like to pretty much, I want you to take a look at this quiz, a very interesting quiz, and it's pretty conceptual, and again, we select the correct free body diagram of particle A. Again, look at all the forces, look at all the angles, and look at the way it's shown. I think right away you can eliminate this guy. Right away we can eliminate this guy. They're not complete. We're left with 2 of them. This guy is also not complete. And again, right away you can spot correct answer is D, because it shows all the forces are shown here, all the unknowns and knowns, correct angles, and all that is shown here. So that is the correct free body diagram of particle A. So there's another attention quiz. Remember, we usually have 2 of these. Okay, so using this free body diagram of point C, the sum of the forces in the x direction, sum of the forces in the x is what? Use a sign convention of plus, that is in the to the right of the page. So f sub 2 sine of 50 degrees minus 20 is 0. F sub 2 sine cosine of 50 degrees minus 20 is 0. F sub 2 sine of 50 degrees minus f1 is 0. F sub 2 cosine of 50 plus 20 is 0. So first of all, the direction of the 20 is negative. So right away we would eliminate this answer, and we also eliminate this one. We're left with 2 more answers. So if we would like to find the x component of F sub 2. Again, remember this is for the sum of the forces and the x is 0, so we are not worried about F1. It's really out of the equation, but we are concerned with the x component of force F2. The x component of force F2 must be F sub 2 cosine 50 degrees. So this is the correct answer. We can also eliminate this one. So the correct answer is B. That brings me to the end of the lecture. As always, if you have any questions, comments,